I think I can at least start to introduce Elena. So it's a great pleasure to have Elena today as a Quid Ultra speaker. And Elena is a theoretical astrophysicist. She has been working on a very broad range of different topics involving, most of them involving gas and stellar dynamics around compact objects and gravitational wave astrophysics. And since 2011, she is based in Leiden Observatory, but she has traveled quite a bit among different countries and continents in the previous years. She received, in fact, her PhD in 2005 from the Institute of Astronomy in Cambridge, where she has developed her structured jet model, which is now very instrumental to interpret the emission following, for instance, double neutron star mergers. And then she moved to Boulder, to Colorado, holding a NASA Chandra Fellowship in 2006. And she started to be heavily involved in the preparation for, in the theoretical preparation of the ESA mission LISA, where now she has a very prominent position as a science team co-chair. And this is actually due to her very important investigations on gravitational wave sources, such as supermassive black hole formation and evolution, and also white dwarf binaries as galactic tracers. And then she went for a postdoc position in at the Hebrew University, where she started to work on yet a different topics on tidal disruption events and on multiband modeling of the thermal emission from of disk formation simulations. And finally, she has very recently been awarded an ERC Consolidator grant for her work on the galactic center and stellar dynamics in the galactic center and dark matter halo distribution with different dynamical tracers. And this will be mostly what she will be presenting us today. And so I leave the floor to you, Elena, and thank you again for having accepted our invitation.
Okay, can you see my screen?
Yes.
Okay, so thank you very much, Rafael. It's a pleasure to be giving this colloquium, and I regret not to be there in person. The logistic didn't work out this time, but I'm really looking forward to come and visit in the near future. So as Raffaella said, today I want to present my Vega project, which stands for the Velocity Extreme Galactic Astrometry project, a project I've been working on for several years now, and is coming to fruition with the ongoing Gaia data releases. So this project, so the talk is gravitational wave free. So I will only talk about basically optical observations only. So the project has addresses two sets of science questions related to the Milky Way, and in particular Milky Way halo, and on the so we are talking about kiloparsecs scale, and on the other extreme of the scale, a question on the formation and evolution of the galactic center. So we're talking about actually phenomena happening in a parsec scale. And I will show that the link are the investigation tools that I'm using, which is hypervelocity stars. But let's start from the galactic center. So in our galaxy, now has been actually is a Nobel Prize certificate that there is a supermassive black hole with a mass of 4 million solar masses, or at least the dynamics of stars around the supermassive around these point sources point toward the direction of having a supermassive black holes of this mass. And one of the science question here is how the galactic center was assembled, which is intimately linked on the question of how supermassive black hole grows, in particular in galaxies like ours that have been more or less quiescent. Perhaps we had one major merger in the past, maybe in the last 10 giga years or so, but probably not more than one. So there are various theories. Some involves continuous like accretions of like inflow of gas, and so the stellar population has been born in situ, perhaps in tori or in disk structures. Others instead maintain that the galactic centers have been instead assembled by globular clusters by stars that have been brought in with globular clusters that have been subsequently dissolved by the tidal field of the supermassive black holes, or can be also a combination of the two. So the way astronomers try to address these issues is by modeling, by benchmarking theoretical predictions with observations of the stellar population of the galactic center, in particular their distribution, isotropic and isotropic, their masses, ages. The main challenge in trying to understand how galactic nuclei hours and in general are formed is that observing directly at the galactic center is extremely challenging, in particular studying individual stars, is particularly challenging because of the enormous dust obscuration, 30 magnitude in the V band, and also stellar crowding. For instance, Gaia can't observe the galactic center directly. Therefore, so we are limited in the type of observations that we can make directly. For instance, we can individually study only extremely massive stars in the galactic center with masses greater than 10 solar masses, 15. And therefore, we have a biased view of the stellar population in the galactic center. And we only know of a couple of binaries, for instance, and they are both extremely massive binaries. So my strategy is different and is complementary, I would say. So I'm not looking directly at the galactic center to find clues on its stellar population, but actually I'm looking up at the halo, looking for hypervelocity stars. So hypervelocity stars are galactic center stars, but have been kicked out from the galactic center following a dynamical interaction with Sagittarius stars into unbound orbit through the halos, unbound or marginally bound. These stars were actually predicted in 1988. So Hills actually said, a signature of a supermassive black holes in our galaxy will be the presence of such stars in the halo. And the first star was observed in 2005 by Warren Brown. So how can we gather information about the stellar population, of the content and dynamics of the galactic center? So we can gather direct information by spectroscopically actually studying these stars in the halo, because these stars are in a more telescope accessible, telescope friendly part of the sky, so we can individually study them even if they are of lower mass, so more common, maybe 1, 2, 3 solar mass stars. Another way to obtain information is by statistically model their distribution in phase space, so velocity in space, and also masses, for instance. So, and here I need to say a little bit more about the models than the injection models. There are like a host of models to eject hypervelocity stars, and they all almost all involve at least 3 bodies. So they all tap the enormous kinetic energy of hypervelocity stars. It always comes from the potential energy of the supermassive black hole. The standard model that was originally proposed by Hills concerns a binary, stellar binary, which is tidally separated following a grazing encounter with the black hole. One star remains bound to the black hole while the other is ejected. Okay, we know that such mechanism do work at some level. We know it because it's very similar to the mechanism that give rise to tidal disruption of stars, of which we see flares in other galaxies. So instead of tidally separating a binary, in that case, we tidally disrupt a single star, but the mechanism that injects these stars into these very radial orbits grazing the black hole is the same. And the rates of TDs is at least 10 to the minus 4 per year or higher. And so we reasonably expect the rate of hypervelocity stars coming from this mechanism to be ballpark around this number. But we know it does depend on the galaxy, as I will say in a second. So in a series of papers, we, together with collaborators Rem Sari and Shio Kobayashi, we developed an analytical formalism to describe the trajectory of this 3-body system, binary and black holes, and also the evolution of the energies. And we have used what is called the restricted 3-body formalism, which is used, for instance, very successfully to determine the trajectory of the asteroids in the solar system, where the 3-body will be the asteroid, the moon, and the Earth. So in particular, we derived an analytical formula, which is also accurate for the velocity of the hypervelocity star. And we showed that it depends on the, in this particular way, on the separation of the binary A and on the masses of the star. And there is only and the geometry of the encounter, retrograde, prograde, or which phase, and so on. Everything goes in, is factored out into a numerical factor, which turns out to be of the order of unity. And this is very powerful, this formalism, because it allows us to explore a very large parameter space, which will be very hard to explore with only a 3-body simulation, for instance. So the bottom line here was that the velocity distribution depends mainly on the parameter of the binary. And in this particular model, the ejection is assumed to be isotropic because stars comes from, they don't have a preferential direction of arrival. They come from everywhere, the central nuclear star cluster. And so there are special distribution in the halo. If it's anisotropic, is only given by the galactic torque. For instance, the disk could torque the direction, the trajectory of a star towards the disk. If the angle it's very close to the disk. Okay. On the other hand, the rates, so how many, and that I touched upon at this point before, the rates of the stars, so how many we can see. If you think about it, these stars are like anomalies. Stars are happily going around the galactic center, whose potential is mainly dominated by the black hole. But doing so, they actually suffer microscattering from adjacent stars. And therefore, its angular momentum is slowly diffusing until they develop such a low angular momentum that their trajectory is radial, and they follow very close to the black hole. So the rates, so how often this happens, does depend on the stellar distribution. For instance, let's say that the galaxy has had a recent merger. So let's less than maybe 1 giga-year or so. We expect the galactic center nuclear star cluster to be non-symmetric. And more non-symmetric it is, the higher is the rate of these stars. Instead, if the stellar distribution is very spherical symmetric, then these orbits, phylocentric orbits, are rarer. So ballpark, in highly distorted nuclei, we expect rates as high as 10⁻³ per year. And instead, in spherically symmetric nuclei, rates can be 1 every million year or so. We can also derive actually the stellar distribution, the radial stellar distribution in different direction, theoretically from the rates. Okay, now we talked about theory, and now I'll go back to observations. Okay, so far, let me take this. Okay, wait. Okay, otherwise I don't see well my screen. Okay. So observations. So far we have less, I would say less than like 15 hypervelocity stars. They are all, and this is a selection of the search, they are all B-type star, late B-type stars, so 3-4 solar masses. And there is a sample that was found in the SDSS, and they are all in the outer halo with velocity greater than the escape speed. In the inner halo, we only have one hypervelocity star, but this star is very well measured, so the kinematics is known very well, and its total velocity is 1,750 kilometers per second. It's at 9 kiloparsec from the galactic center, and it's A-type star, actually. It's a little bit of a lower mass than the ones in the outer halo. Then, together with my now ex-PhD students, we determined the previous 2 Gaia data releases. So Gaia is a ESA mission that is basically tasked to observe 2 billion stars in our galaxy, measuring the proper motion in the sky, parallaxes, which is a proxy for distance, and for a subset of these stars, which currently is 7 million, Gaia also, the Gaia catalog also provides radial velocity. So for 7 billion stars, we do have, which is the greatest radial velocity survey ever produced. We have full 6D information. So we determined this 7 million stars with full 6D information. And of course, using quality cut, looking only for unbound stars, and we found none. So in the following, I want to use these two sets of informations. So on one hand, the fact that we have observed one hypervelocity stars in the S5 spectroscopic survey in the south, which this velocity, mass, and position. And on the other hand, I will use the constraint that we have found no hypervelocity stars in Gaia 6D. So to interpret this observation, we have created a statistical framework. And let's start from the Gaia non-detection. We used the theoretical model I explained before to construct the likelihood of the data given a model. Using, of course, this model, but also the characterization of the Gaia survey. So in each position in the sky, how well we can observe a star given its magnitude and color. So using this likelihood and flat priors, we were able to derive for instance, this joint posterior, which I'm showing here. And I will go to the next, that I'm showing here. So on the y-axis is the IMF, the mass distribution of stars in the galaxy, which we parameterize as a power law within this K. And on the x-axis are the rate of hypervelocity stars. The diamond-shaped points are the lowest. So 10 to the minus 4 as a rate has been chosen here in this figure as a guidance because it's the rate with which we observe tidal disruption events in other galaxy, so it's just a guidance. But the three diamond are actually the lowest is the Krupa IMF, the second higher. I don't know if you can see maybe my mouse here. So this one is actually a IMF inferred from direct observation of the galactic center. In fact, the galactic center, at least from the partial measurement that we have, seems to be a top-heavy, seem to have a top-heavy IMF. And there is even a more extreme top-heavy IMF here with index minus 0.5 that has been claimed from direct observations. Okay, so on the background is our result of our joint posterior. So it's clear that we can exclude at 1 sigma, and which is the thick line, and the 2 sigma, which is the thin line, the upper right corner. So the ones with very, very extreme rates, very high rates, 10 to the minus 3, 10 to the minus 2, and extremely top-heavy IMF, that corner. So the fact that we haven't seen unbound stars with certain quality cut in Gaia exclude that the rates are very high, and at the same time, the IMF is very top-heavy. This is because the more top-heavy it is, the brighter the more likely is to eject the bright stars that can be therefore seen. Okay. Now we do the same thing, but we now jointly interpret this non-detection and, on the other hand, the detection of what is called HVS1 in the S5 survey. And this is the result. And go back and forth. So as you see, the fact that we have detected one star with such extraordinary velocity, so this is it's a 3 sigma outlier, I would say, allow us to exclude, on the other hand, very low rates and very non-top heavy IMF. And so we are left now, these are the first, let's say, indirect constraint of the IMF in the galactic center. And we are left with this degenerative stripe between IMF and the ejection rates. So, which is still consistent with the top-heavy IMF measurement by Liu et al. 2013. Well, next Monday, there will be Gaia Data Release 3. And we are going to determine the new sample of hypervelocity stars with radial velocity, which will be 5 times larger. So our sample will be of 35 million stars. And we will do this exercise and we will see how the constraint we will shrink again. So what are the next steps? One, I already said, my ex-student Tommaso Marchetti and my current student, Fresden Evans, are on to Gaia DR3 in 6D. So I show Raffaella before that we already have the draft ready, and we have, because we have all the modeling in place and the data mining routine. So we're only waiting for the catalog to appear. My PhD student is Silverbeeren. He's looking into the rest of the Gaia catalog. The rest of the Gaia catalog does not have radial velocity information, right? So we are developing different data mining approach to find candidate hypervelocity stars that will be followed up within the WIV consortium. Hypervelocity stars is a priority target for WIV. And I'm part of the low resolution high latitude survey. And WIV will start its operation. So WIV is a multi-object spectrograph. I'm sorry, I'm giving to. So WIV is a multi-object spectrograph on the William Herschel telescope. And will start its science operation this coming September. Was supposed to start last year, actually, even earlier than that, but both the pandemic and the volcano on Canary Islands implied that the WIV operation had to be postponed until this September. So let's hope that nature is on our side this time and the observation will start. Finally, in September, Zephyr Penoyer from Cambridge University will start as a postdoc in my group, and we will do the next step, which is the following. I want to go back to my science question. What does it mean for the origin of the galactic center, these particular constraints? Which models for the formation or assembly of the galactic center we can reject, and which one instead we can favor? And some work has already been done by me in the past, but Zephy Penoir, who is an excellent mathematician and dynamicist, will bring this forward. So this was all for the galactic center. But I'm not only interested in using hypervelocity stars as a tracer of the galactic center stellar population, but also as a tracer of the mass and massive distribution of our galaxy. This is because they originate from the galactic center, but their trajectory is through the halo. So it's clearly the trajectory, their deceleration is shaped by the mass profile in the halo. Also, if you think of it, it's we have a great advantage because we know where hypervelocities are come from. So in principle, so we know the initial phase space. Then we observe the phase space of a hypervelocity star in the halo, and then we know from Wheeler's theorem that there is only one trajectory going through these 2 points, which uniquely determine the potential. Okay. This is in theory. Of course, then is how well you can determine the position and velocity of the stars comes into matter and gives the uncertainty. Why is it important to know the mass and mass distribution of the galaxy? So this question is within a broader context in which we use observation of the galaxy as a benchmark for models of formation evolution of galaxies, of the nature of dark matter, of modified gravity theory, and also to understand the baryonic physics, like star formation, for instance, by comparing observation to what the outcome of simulations. Okay, coming back to my specific question. Don't we know the Milky Way's mass already? So the answer is in this plot. So here I'm plotting the total mass as constrained by different dynamical tracers. So the issue is that most of the mass is, as you know, is dark. Is in a component that we call halo that goes out to 200 kiloparsec, and luminous tracer that can tell us about the distribution of the dark mass becomes rare and rare. After 10 kiloparsec, these tracers becomes more and more sparse, giving us like a fragmented knowledge of the halo mass distribution. So people have been using different tracers, globular clusters, dwarf galaxies, halo stars, hypervelocity stars, stellar streams. Stellar streams are globular clusters or dwarf galaxy that have been tidally disrupted by the tides of the Milky Way into elongated stream of stars. Okay, here, so here you see a collection of this determination. So the uncertainty is a factor of 2, 3. But what worries me is that there are systematic differences between the measurement. For instance, let's see the stream. This will be the cyan points. This are both measurement with streams. And you see that these measurements do not overlap within 3 sigma one to the others. So they are really systematics within the different probes, but also with the same probes. if different modeling techniques are used, for instance. And the problem is that prediction from cosmological simulations differ significantly within this range. And this is what have been given rise to conflicting claims. Lambda CDM is not good. Yes, Lambda CDM is good. All depends on which mass, total mass you pick, for instance. Okay, so what is my strategy? So what I thought, what I think is a very, it's a novel, but a very promising way of approaching this is by borrowing a method of combining probes that been successfully used to determine the cosmological parameter with high redshift probes, supernovae, BAO, and so on. My cosmology colleagues showed that if you combine probes, actually, and you can, and you ask, oh, I want a universe that simultaneously describe all the probes simultaneously, you're more likely to get a robust answer. So in the same way, I want to combine probes in order to get a robust answer on the mass and mass distribution of the Milky Way. I'm not much at this stage. I don't think we need to go for unrealistic precision, but really we need to understand our systematics and aim at a robust answer. In particular, the probes I want to use are hypervelocity stars on one side and stellar streams. Why these probes? Because they, as I shown this in this cartoon, which is based on actual measurements, because these two probes are orthogonal. They span a different part of the parameter space. In particular, hypervelocity stars, being unbound stars, they are sensitive to a combination of mass and scale radius, which has the dimension of an acceleration. So they are sensitive to a given effective deceleration of the halo. On the other hand, stellar streams are bound stars, and they are sensitive to the mass enclosed within their orbit. So this determination of these constraints are orthogonal and allows me to more likely get a robust answer. Okay, what about hypervelocity stars? So this is a simulation of what we hope to obtain with Gaia Data Release 4, where we think we may have at least 100 hypervelocity stars with precise kinematic measurements. So this is okay, an upper limit of what we can obtain, because I don't vary here the parameters pertaining the ejection. So here I'm assuming that I know exactly what the ejection mechanism is and all the parameters pertaining the binaries. And I'm only exploring different potentials. So on the y-axis, there is this the deceleration parameter. So mass width, in particular here is mass width in 20 kiloparsec divided by R20. And on the x-axis, instead, there is the halo axis ratio. The halo is described as a spheroidal in this model. And you can see that with 100 hypervelocity stars, we can obtain even a sub-parsec, sub-percentage precision, which of course there will be smeared out once we also run our Monte Carlo search over the ejection parameters. But still is extremely promising. And we don't find any particular bias. in order to eventually construct the joint likelihood, I also needed to understand better the systematic pertains to the streams alone. And this is, has been Stella Reynos' PhD thesis. She will graduate, she just submitted her thesis, she will graduate in September. And together we wrote 3 papers exactly modeling the theoretical with mock data, but also real data, trying to constrain the mass distribution of the halo, but in particular dealing with the systematics of our method. Since this will be a talk in its own, I will just leave it here, and I want just to show that this is really the right moment to think about streams, because with Gaia, now we already have 97 known streams, and this will for sure explode with the next data releases. Thank you.
Thank you very much, Elena. That was really super interesting, and I'm sure and I hope that there would be many questions. Well, I don't know if there is someone who has already a question for Elena from remote attendance from Kazu here, but in case I can start, I have one.
I do have a question.
Sorry?
Okay, if you want to go,
go ahead. No, you have go ahead. Please.
Okay. Okay, I wanted to ask you, what do you think could be the reason for a top-heavy IMF in the galactic center? I mean, is the IMF top-heavy because the heavy stars sink to the galactic center more easily after having been formed in other places, or maybe because the particular conditions of the galactic center influence the star formation process in the molecular clouds to the point of producing a different IMF?
Yeah. Okay, so this is an excellent question, and it's highly debated. I would say the mainstream answer is that heavy star, that the star formation in the galactic center in situ proceeds in a different way than outside. Within the sphere of influence of the black hole, normal molecular clouds will be torn apart because the sphere of influence is a few parsec, and this is also the size of a molecular clouds, and you can do like a calculation and see that there will be that the self-gravity of the clouds won't be sufficient to collapse. Given the presence of the tides of the black hole. So we know that star formation does not proceed through spherical collapse of clouds in the galactic center. What people think is that gas comes in, perhaps, and form actually with some angular momentum. So you form a disk, and stars are born within disk because fragmentation can occur in the vertical direction, and the suspicion is that in this mode of star formation, bigger temperature and density are such that the IMF is more top-heavy, but I think that is still up for debate. Also, if it's a top-heavy.
Okay, thank you.
Other questions? Kazu has a question. I think you can get closer to
Yes, thank you very much. Very nice talk. And so let me start with the very basic question. So you mentioned the hypervelocity stars. The definition of a hypervelocity stars are those ejected from the Sagittarius A star. But how did you sort of pick up those stars? How do you identify those stars are actually ejected by the Sagittarius A star? Just from the fact the stars are unbound, or is there any other criterion?
So, yeah. So the question about how we identify hypervelocity stars.
Yes.
Yeah, which is an extremely good question, because it's because in principle, stars of any masses and any velocities go down to zero can be ejected by any of these mechanisms that I just fleshed out, because it's a continuous process. Okay. Low velocity star can be confused, can be also bound to the halo, so can be confused with halo stars very easily. And therefore, when we look for hypervelocity star, we only look for unbound stars. So it's an observational definition. Moreover, if we look for unbound stars or like 500 kilometers per second stars, so nearly bound, we always look for young stars, so stars that you do not expect in the halo. So that's why our sample, the current sample, is biased towards late B-type stars.
Okay.
Yeah.
But the ejection can be by another mechanism, for example, in the star clusters, some dynamical interaction, and some star can be ejected. So can you sort of conclude those stars are ejected actually by Sagittarius A star?
What is the alternative you mentioned?
My question is how can you know those hypervelocity stars are actually ejected by Sagittarius A star?
Okay, so this is from the theoretical point of view. To escape the bulge, you need velocity at ejection that exceed 800 kilometers per second. There is no mechanism.
Only by the central supermassive star. Okay. And
yes.
So another a bit related question is because the hypervelocity stars are by definition hypervelocity, so they crosses the halo in not so long time. That means we cannot know the path to the past ancient history of the galaxy build-up. So, but how the distance past is your analysis sensitive?
So we are since we are selecting very high velocity stars as a selection bias, basically we are looking at flight time of at most 50 million years.
50 million years. Okay.
So we are looking at the halo today, and basically the galactic center really today.
Okay, thank you. Yes.
Yeah. But somehow, if I understood correctly what Kazu was aiming to, somehow, of course, your technique is sensitive also to the past history, the past assembly history of the halo, because of the leftover distribution and the property of the distribution of stars in the halo itself. I mean, so you are sensitive to the leftover of the past history of the Milky Way.
For example, you constrain the IMF slope and also the ejection rate. So those sort of values are sort of valid for, say, only for the 50 million years, or even so, can you know that even even so the far distant past? No.
We need to go. So the approach is the following. Now, since we want to find as many as possible, and with a more clear identification, we are looking at very fast stars, and then we will try to lower this threshold. And the more we lower the threshold, the more in the past we go. Does it make sense? Because the lower flight times. But then identification can become more ambiguous. We still have to look at late B type stars, which have a lifetime of 300 million years. So we will be limited by the lifetime of the star.
Yes.
Right.
But then maybe we can go to high metallicity star and then go down in mass. So the more we learn, the more we can so use the metallicity to distinguish them from halo stars. If we think, as now people think, that the galactic center is a high metallicity environment.
So any other questions from the audience, from remote participants? See any? So if not, we'll take advantage of one. So I'm I'm not an expert at all of these very interesting techniques, but I'm wondering if you can give us a clue of why you would expect about 100 hypervelocity stars in this new Gaia data release. How do you base this estimate on?
Yes, so from the current constraint, so seeing that we haven't seen stars in the past data releases, and given the stars that we have observed, then there is a range of expectation for the future data releases. So it's basically based on the model that I described today and the current observational constraint forecasted.
Okay, and another question is why SDSS has been definitely more sensitive to these hypervelocity stars than other surveys so far?
Yeah, so so the strategy that has been used there is to photometrically. So basically the only information that we use are photometrically select B-type stars faint, so that it's far away and blue. So the SDSS had these bands to do so, and also the biggest area. So, okay. Now I'm trying to do the same technique that Warren Brown used for SDSS with Keats. It's a survey that it's the precursor of Euclid, and then I want to use Euclid as well, because we can go in the south, where SDSS is only north.
Interesting. So a lot of work to be done in the next few years. So if I don't see other questions from the audience, so if you don't have any other questions, Kazu, so I will thank very much Elena for her time and for this beautiful talk, and of course I really look forward to having you in Rome in person soon. I hope. So thank you, grazie mille, davvero.
Grazie a